Hello and welcome back to video 2 of chapter 15, acid-base equilibrium. This is where we left off. We had just determined that after we added 50 milliliters to 0.1 molar sodium hydroxide to our solution, that it was at its equivalence point. Now remember, equivalence point does not mean it's always going to be a pH of 7. What it does mean is there are equal moles of each, so they all turn into water, essentially, and you have a salt left over. So part of our salt that's left over is our acetate ion. Well, since the acetate is essentially a conjugate of my acid here, it would be a conjugate base, it acts as a weak base. So my conjugate base here is actually going to make it slightly basic. And we have to calculate that by, the wrong thing popped up, sorry, doing a little icebox here and saying, okay, what I had was my acetate ion. Here's what it's going to do. It's going to hang out with the water and turn a little bit of our acetate back into an acid and have these hydroxide ions floating around. The reason this happens is because that's what a conjugate base does. It makes the solution more basic, or it shifts the equilibrium towards being basic. We blacked out the gray because remember, it doesn't matter if it's a liquid. What did we have from our last slide here? Well, we had that 0.05 worth of my acetate ion was in solution. And I calculated that 0.05 by this little equation down here. On the last slide, I had that 5 millimoles were produced. Well, all I did was what we've been doing before, and I divided it by my total volume right now to get out 0.05 molar. Okay, if you feel lost, I want to go back a little because I think that was confusing. I have my 5 millimoles here. The reason this happened is because this is a conjugate base, the leftovers of my acid. This is an important piece of my reaction, unlike things like my water and my sodium. So I'm taking this 5 millimoles with me to the next slide. And what I'm doing is I'm turning that 5 millimoles back into molarity. Because remember, ice boxes can only use molarity. Our stoichiometry box used millimoles. So I divided it by my total volume right now, which I got from up here. The amount of NaOH I added plus my initial amount of that acetic acid I put in from the original question. And I got out my molarity. Then I plugged my molarity in my box, ice box. Molarity, we know it's going to shift to the right and produce these things. Why is it going to produce these things? Because this acetate stole a hydrogen from my water in order to get back to how it wants to be, which is being acetic acid. When it stole that hydrogen, it left behind a hydroxide. So ironically, when we made an acid, we released a base. Remember, everything in chemistry is backwards. Which way is this going to shift? To the right. Calculate for my x like usual. But use your 5% rule and make sure you check it if you do one of these on the exam. Pretty sure I forgot to do it again earlier. So, to solve for my x here, what I'm going to do is I need to take my Ka from earlier and plug it into this equation that's Kb times Ka equals Kw. Remember that? We talked about it last chapter. What I'm trying to do is convert this to Kb. Why do I have to do that? Because I'm talking about my base stuff over here. I'm talking about my solution being basic. So, if we were going to summarize the steps here, first, we did our stoichiometry to figure out what was going on in our reaction. We figured out it was at the equivalence point. Because it's a strong base, weak acid, we know that what's going to happen is it's going to still be slightly on that basic side. So, I had to calculate now the number of OHs left over in solution. I can't use a Ka if I'm talking about a basic solution. So I'm going to convert it to a Kb. So I took my Ka and my kW and plugged it in to get kb. Hope that makes sense. Here's my kb. I didn't show the math, but it's this divided by this. Gave me 5.6 times 10 to the negative 10. Where did I get all this junk? Well, it's right up here. X squared, because they're my products, they're on top, reactants on the bottom, and I'm solving for X. Now I would do my 5% rule, figure out, yeah, it was less than 5%. Two options to go from here. I can either negative log to get my POH or solve for H plus. I did my negative log of POH, and I got a pH of 14 minus 5.28. So 5.28 was my answer to this. I have to subtract it from 14 to convert it to pH. Okay, so my pH is 8.72. We're at the equivalence point. This proves that at the equivalence point it's not always 7. I'm a little bit above 7. That's because it's a strong base, so naturally my acid's not going to react equally with my base because my base is so much stronger than it. Okay, so we got our pH. Now, I just said this, it's always greater than 7. Now we have 2 pHs so far, or 3. Can't even keep track. We had our initial, we had our first milliliters, and now we had our 50 milliliters. We're getting there. Now we have 60 milliliters. So now we're going past our equivalence point. What do? Same exact thing we've been doing. Okay, we're adding more OH negative to make it even more basic. Same process as before. Turn it into your millimoles. This over here is going to be my 60 times my 0.1 to get 6 millimoles. Plug it into my bra box, my stoichiometry box, and subtract. This time, my limiting reactant is going to be my acetic acid. It's all used up. I've reacted all of it. And I have 1 millimole of OH negative left. But in the process, I created 5 more millimoles of acetate. So, both of these things are left over. NaOH is such a strong base that it dominates the reaction, and we actually don't even have to calculate an equilibrium thing, because we should know that a strong base will overpower a weak acid's conjugate base, because that makes it a weak base. So actually I can take a little shortcut here, and all I have to do is use my hydroxides from my NaOH in order to find the pH. But remember, this isn't a concentration right here, this is in moles, so I need to convert it. I need to take my 1 millimole, divide it by my milliliters, and get out my molarity. It's really small molarity. Take the negative log, and I have a POH of 2.04. As usual, subtract it from 14, and I've got this pH of 11.96. That's still pretty basic. Okay, so that was how we go through a strong base, weak acid reaction. I know this is overwhelming, but you guys can do it. I swear you can. Take it step by step. Go back through this video and try this next one. It is on page 776 in your book, and it's number 55, but it's exactly like it says right here. You should have all the information you need, even without your book. So try this one out, and we'll go over this one in class on Monday as well. Okay, so one little more thing here to talk about a strong base, weak acid. Here's what our pH curve looks like. It looks a little different. Remember how steep it was before? Well, the reason this is happening is I can still see right here I'm starting with a weak acid because it's above 1, and it's at 3. What I did was I added some base. It hit this little zone right here. What did I call this zone? My buffer zone. If I had a question that asked me to find a pKa, I could go over and look at my buffer zone and do my negative log of, in this case, 4-ish, and see what I get out. Okay, then I go up, and I really didn't have, as specific a point in this one. Before, I could really look and see my milliliters, but I'm estimating that this is my middle point on the line, and it said about a 9. Well, if you remember, we were pretty close to a 9, I think, when we calculated our equivalence point for our problem just now. And then when we get past our equivalence point, it levels off and becomes really basic. So the reason this happens, you guys, is because, like in that problem, my conjugate base from my acid released some OH ions. When it released hydroxide, it shifted up as far as pH. So just think of it like strong base plus the conjugate of a weak acid, which would be a base, is going to shift my line up. So what do you think is going to happen if we have a strong acid and a weak base? Just the opposite, right? It would shift it down. So these graphs are actually really helpful when you think of shift. Okay, so I have about 4 minutes left of my video to run through this strong acid weak base titration with you. It follows the same exact steps, okay, but kind of in an opposite order. So I'm going to go quick. You might have to watch this part again. So initially, before I add my hydrochloric acid in this problem, I have this weak base here. Well, I know that that doesn't disassociate completely, so I'm going to do what we're used to and do a little ice table, plug in my molarity, figure out the direction of my shift, assume that my x's don't matter, plug it all into my equation. Note that we're using KB here. Plug it all in, solve for x, put it in my negative log. Note that this is POH, so once again you have to do the 14 minus that number to get out 10.98, almost 11 for my basic solution here. Now it asks after 25 milliliters. This is when I need to really start thinking about what's happening. I'm adding in hydrogens here. So what should my pH do? It should drop. So what I'm going to do is convert them to millimoles like we've been doing and plug them into my stoichiometry box, my bra box, or whatever you want to call it, and determine my shift again. Well, this side's going to subtract 2.5, that side's going to add it, and in this case my H is going to be my limiting reactant. Follow the same steps we've been following by plugging these guys in, figuring out their molarity, and at this point you can either do an icebox or the shortcut Henderson-Hasselbalch equation and plug these guys in. Remember, if you do your shortcut with a POH situation, you still have to solve for pH by subtracting the from 14 in order to get this pH of 9.26. So always think to yourself, does my number make sense for pH or POH? Because it should be opposite. You know, really think about that. Okay, so then I add 50 milliliters, and guess what? As per usual, we ended up at equilibrium, or at the point where my moles are equal. But I have this extra 5 over here acting like an NH4. Well, hey, that's the leftover on my base. So what do I call that? I call that a conjugate acid. And my conjugate acid's going to shift just a tad bit for it to be more acidic than expected. So I'm at my equivalence point, and I have all these major species in here. But what's really important to me is that NH4. What is that NH4 going to do? Well, it's going to shift me over, and because of that I need to calculate its molarity. So all I did was our usual molarity calculation, and I'm going to plug that in my icebox. And what's going to happen is this NH4 is actually going to lose that H because it wants to get back to NH3. And when it does that, it's going to produce some H plus or some hydronium. Remember, we can see it both ways. So do your icebox here, figure out your shift, and solve for X. The only difference is we were provided with KB before. So I need to convert it to Ka because now I'm talking about acids. And I'm going to use that Ka, here's my answer, 1.0 times 10 to the negative 14th divided by this gave me this number. Solve for X, plug it into your negative log, and now we're talking about pHs again. So it's slightly acidic. I'm going to do the same exact thing that I have been doing for my 75 mils here. Plug everything in, figure out my shift. This time my limiting reactant's the NH3, which means my solution's totally acidic. Because of that, I really don't even have to do my equilibrium calculation because HCl is so strong that I can just plug him in, do the negative log, and get my pH out. So, hopefully that was good practice for you. We'll also do this one in class. If you're up for the challenge, you can try number 56 on page 776, and I'll see you Monday. Bye.